Hello and welcome to section 2.3 of our linear algebra notes. Today we're going to talk about characterizations of invertible matrices, and basically we have one giant theorem. A lot of the proof of this is going to happen during class, but I just wanted to give you guys a sense of how this proof is going to go. So we have a square matrix, an n by n matrix, and then we have a whole big list of things that are all equivalent. These are all equivalent to the matrix being invertible. So we have things like it's row equivalent to the identity matrix. It has n pivot positions, and so on and so forth. And many of these things are only equivalent to being invertible if the matrix is a square n by n matrix. So for example, the equation ax equals 0 has only the trivial solution, means that A is invertible when A is an n by n matrix. So the way that we're going to do this proof is, first of all, we're going to prove that like one thing implies another thing implies another thing, and so on. And so we kind of start out with the notion that part A implies actually part J. So this is saying that if A is an invertible matrix, then there exists an n by n matrix C such that C times A equals the identity. So when we write this arrow, that means implies. And we have one other arrow that we can draw, and that's a double arrow. And this arrow means if and only if. And we've seen this before. Basically, if we write A if and only if B, well, that means that A implies B and B implies A. So the arrow goes both directions because it goes both ways. Okay, so what we're going to do then is we're going to build sort of a web of implications. So A implies J, and J implies D. D implies C. C implies B, and B implies A. So that's kind of a little circle there of implications. So once one of these is true, you know that all of them are true, because like if you know D is true, well then that implies C, which implies B, which implies A. And so D then implies A. You just have to go through other intermediaries to get there. And then there's several other things that kind of branch out from this cycle. So we also have a little bit of a triangle that says A, in fact, implies K, which implies G, which implies A. And so now anything on here is true, because if J, like let's say we know J, then that implies D, implies C, implies B, implies A, implies K. So J implies K. And we can keep going like this. We have G if and only if H, if and only if I. And so the if and only if means you can both directions. Again, if you know I, then you know H, then you know G, then you know A, and then you can get to K or to anything else. Okay. We also have D if and only if E, if and only if F, and then we also have A if and only if L. And I believe we have everything on here now. We have A, B, C, D, E, F, G, H, I, J, K, L. Okay, so this is kind of the overall structure for the proof. And now we want to talk about how we'd actually go about proving these things. Well, you prove each of these little arrows. So let's do one together, and then the rest of these we're going to do an activity in class to kind of start to understand them better. Okay, so A implies J. So that means we're assuming A, and we want to get to J. We want to get to a n by n matrix C such that C times A equals the identity. So we start by assuming A. So we assume that our matrix capital A is invertible. And that is our condition A. Okay, and now let's just let C equal A inverse. We know A inverse exists, so we're going to let C equal that. Well then, if we do C times A, that's A inverse times A, which equals the identity. So J is true. And I'll go ahead and tell you what we'll do in class is I will give you this bit of each of the proofs, and you'll want to figure out what that statement is, what that justification is actually proving. Okay, there's a little bit that we can do with this involving linear transformations. So I'm going to move on to that. And here we go. So first of all, we want to kind of understand when a linear transformation is invertible. And so first we're giving a transformation that rotates vectors by 90 degrees clockwise. And if you'll recall, to find the matrix for a linear transformation, we want to know what that transformation does to the vectors 1, 0 and 0, 1. And so if our transformation rotates each of these vectors by 90 degrees clockwise, well, it's going to take this pink matrix and rotate it to pointing down. I'm sorry, pink vector, and rotate it to pointing straight down. And similarly, the blue vector is going to rotate 90 degrees, and so now it will be pointing in the direction 1, 0. And if you think about this as a little like frame, it's almost like you take this little L and rotate that whole L 90 degrees. And now our matrix for the transformation is given by first writing down what 1, 0 went to, which is now x coordinate 0, y coordinate -1, and what 0, 1 went to, which is now 1, 0. So here is our matrix. And finally, our quiz for today asks, is this matrix an invertible linear transformation? That is, can you go backwards? And it also asks you to explain your answer. So we'll stop here and let you think about this and answer your quick quiz for today.